So I'm really pleased to be here and to present you one of our biggest projects in aquaponics, which is called Smart Aquaponics. And Smart Aquaponics is, we are coordinating Smart Aquaponics in the University of Liège and at the site of Jean Blou. So we are developing several systems of production in the context of the research center of urban agriculture. Then we will, today, I will present aquaponics in the introduction as a novel mode of production. Then I would like to present you aquaponics system in our center of research in urban agriculture. This will be the second point. The third point, then I will speak about our big project, Smart Aquaponics. And then I would like also to speak about some other research that we are carried out in our laboratory. Let's start with the first part, introduction. As you might know, there are emergence of new production methods, and their methods are targeting the optimization of the use of resources and also the integration of waste in their cycle and also the surplus. We call them circular economy, if you want. And we also observe that agriculture can participate to the conservation or the restoration of biodiversity. And more recently, there is an establishment of local production. And if we go further in detail, we observe a relocalization of production in urban and peri-urban areas in order to feed the cities. Aquaponics, it's a new system in our world, even if it is employed for many, many years in ancient culture. But the modern aquaponics, it's about 30, 40 years ago that we start again. And it's a production which is combined recirculated aquaculture system and also hydroponic. And the idea is to have an interaction between the fish, the plant, and also microorganisms like bacteria, which are able to fix nitrogen. And the idea is that with this beneficial interaction, we will have a decrease of environmental impact of the production. If you look, for example, at hydroponic system, which is part of the aquaponic system, you see here in the graphic a table where you have the number of water required to produce 1 kilo of tomatoes. If you see in the open field, it's around 60 liters per kilo of production of tomatoes. In really, really modern greenhouse in Holland, for example, it's only 15. So you divide by 4 the number of water you need to grow plants. If we go to the global system, then you reduce water to grow plants, but you reduce also water to rear fish, because normally in an open river, you need per kilo of fish this amount of liter, more than around 200,000 liters. In opposite, in RAS system, recirculated system, you only use 300 to 500 liters. Another point is that thanks to the microorganisms, you can transform the sludge of the fish to become a valuable material. And you can see here the requirement of fertilizer for hydroponic tomatoes per year. It's huge. So aquaponic system can produce fertilizer for the plants. So the production of plants use less or no more chemical inputs. I would like to present now the systems that we use in our Center of Research of Urban Agriculture in Jean Blou. You see here the PAF box. PAF box means plant and fish farming. And it's a container, a marine container with on the top a greenhouse. And you can see the system here with a fish tank, then filter, the sump, a pump, the biofilter, and on the upper floor here, you can see a double bed. And we use it for 8 years now, and you can see the production in terms of when we have a cold greenhouse or a heated greenhouse. And the idea is to employ this PAF box for urban use, for the community in the cities. For that reason, for a few years, we also survey the consumption in terms of water consumption, feeding to feed the fish, and also electricity. Of course, you can see here, for example, the water, and you can see that we use 460 liters per kilo of fish, which is more or less like in the literature. And you can see also that we have also rainwater supply, which is count around 27% of the total consumption of the system, which is good also. There is a second aquaponic system in our center of research, and it is called Suppressive. And you can see that this is a RAS system. We have 3 RAS systems, and they are connected to a greenhouse. And in that greenhouse, we have the conventional hydroponic system. So also in triplicates, drip irrigation, deep water system, ebb and flow, and nutrient film technique system. So you can see that with triplicates, we can obtain really good scientific results, and statistically, we can statistically analyze these results. So for the moment, we are working on that system to study the balance between hydroponics, plants, and fish. And we also work on the mineralization of sludge. Let's move now to the most important part of this session, smart aquaponics. So smart aquaponics, it's an Interreg project, a European project, with the region of north of France, Wallonia, and a part of Flemish region. And you see that there are 14 different partners participating to this project. And we want to develop a tool, an application for education, for decision support and monitoring. Why did we decide to do that? When you see the systems in the world and also in Europe, there are a lot of various systems. Not only the systems are different, but also the goal to develop these systems. In some area, the purpose is education. And you can see here some example in Belgium from, of course, from our university, but also from secondary school, like here, one of our partners, the provincial, it's an institute of techniques. There are also non-governmental organizations working on education. But we have also small professionals working with aquaponic systems. For example, here it's a restaurant, and the chef is really proud to rear trouts, and at the same time plants, and the clients, the customers can enjoy in the restaurant trouts and plants produced just next door outside. And the last figure of aquaponic system, it's industrial. We have a big system in Brussels on a rooftop here which is called big system. And we have also other systems on the floor, which is a really professional RAS system for producing tons and tons of fish. And it's connected to another enterprise to produce 10 hectares of tomatoes. So we have several scales of aquaponic system. So aquaponic systems are diverse. It's a new technology, but until now there is no advanced teaching programs, neither or nor specific tools. So it is very important to foster aquaponics development. How to do that? And this is the reason of developing the Smart Aquaponics project. Please read carefully. Okay, don't worry if it was a little bit too fast. It's just an introduction, and I'm going to explain you more in details this project. So, indeed, Smart Aquaponics will be an application. It's an application with 3 goals. First, training program. Secondly, it will be able to simulate aquaponic system. And finally, and it's really important, we believe that it will be also able to monitor the aquaponic system. Concerning the training program, indeed, we are developing the application as a serious gaming. I'm sure most of you knows what is a serious gaming. Is to learn, and at the same time, it's like a game. And the idea is to develop knowledge step by step. And at the beginning, you will be able to build and to understand how a small system is functioning. And then, thanks to improving knowledge during your training, you will be able to go to develop a professional system. Okay? Then, the second step is simulator. When you want to develop by yourself an aquaponic systems, it's really important that you don't crash your system and you have a good plan of your system. So you can design it in the simulator part of the application, and you can, when you have it, you can simulate different scenarios. Okay? Then, the third point is monitoring tool. The monitoring tool is, I think, very important for professional people, but also unprofessional people. It will help to connect your system and to survey your system. Then you will have information on your fish and your plants, and also on your systems and the evolution of your systems, meaning that you can anticipate crashing and accidents, and it is very important. So, how we will develop and how are we busy to develop the smart aquaponics application. So I will present you the strategy now. First, and it's very, very important, we are building a model which is able to mimic aquaponic systems. But as I told you, aquaponic systems are very different in form, in size, and in goals. So how to do that? The model is indeed a series of boxes, we call them objects. One box will be to simulate, to model fish growth and fish behavior. Another one is for the microorganisms. A third one is for the plants. And what is very important here is that you can plug in and plug out a system. If you plug in, if you plug in a fish like tilapia, then you can plug out the box and replace it by another fish. So it's very flexible in terms of kind of fish, kind of plants, and kind of microbiota. Of course, what is also important is to have a modeling of interactions between these different objects, between fish, tomato, for example, or lettuce, microorganisms. And of course, we can, with a model, simulate the interaction between all these objects. You can have in the fish tank, one fish. So you can monitor and simulate fish by fish, but you can have several fishes, okay? So you can also dezoom your system and have interaction between several different tanks and the microorganism and several different systems of plant hydroponics. So this model is really flexible and able to correspond to different systems. Then, if we go back to the strategy, if we have a model, how can we connect the model to reality? Remember, to the different users at educational level, for the small professional, and for the industrials. Then the idea here is to connect this model thanks to probes that will monitor different parameters for fish, for plants, for water. Of course, we need to acquire all this data from with the parameters we want to survey with already existing different tools. If people here are familiar with hydroponics or aquaculture, they might know, of course, EKS system or Ortimax and so on. And of course, we try to adapt our data acquisition chain to be flexible and to be possible to connect whatever the system of sensing, okay? And you can see here that in some case, we need a bridge between the system and the data aggregator. Sometimes we don't need aggregator. Sometimes there is just different probes or sensors without any system that aggregates them at the beginning. So we take into account all the different possibilities in our project. Then, how far are we in the project? We just finished to validate the model. We are really happy of that. The model is ready. We are now building aggregators, and we put our aggregators in the different systems of our partners in the project. And now we are on the way to validate this aggregator to be sure that it will connect the data from the different systems to the cloud when it will be confronted to the model. And then at the end of this year, we will start and we will launch a beta testing of the application. So if some of you in Europe are interested, please contact us. And we expect to release our application at the end of the project, which is at the end of 2021. So you can visit our internet site, and you can follow us here on our different networking media. Okay. Now I would like also to speak about during few minutes of other research. And we are working, as I told you, from 2012 on aquaponic systems, and we have other topics. And I will present 3 different topics really briefly, just to give you a taste. And the first one is we want to compare aquaponic system and hydroponic system. We work with lettuce, and you see here the variety is sucrine. It's a variety that is really well known in Italy, for example. And we want to compare the growth of lettuce in relation with the water quality. As you can see here in the small, I hope you can see, in the small graph here, this is in red the concentration of nutrient for hydroponic system, the normal hydroponic solution with nutritive elements, and in blue, this is what we find in our PAF box system. Remember the marine container with the rooftop, with a greenhouse on the container. And you can see that the concentration of nitrogen, for example, is much less in aquaponic system, in aquaponic water, than in hydroponic water. And of course, it is also, we can also observe the same for phosphorus and also potassium. So we wonder if the performance of, if the water is able to support at the same way the growth of the lettuce. So we put the aquaponic solution from the PAF box in one system, and in a separate one we put hydroponic solution. Then you can see here that the system, the water here was a complemented aquaponic water. What does it mean? It's this water quality, and we add manually, we add nutrients to arrive at the same proportion as hydroponic water. So we call it complemented water. What are the results? We had a really positive effect of aquaponic. First, and here there is the article, the publication where you can find the results. So aquaponic and hydroponic system had exactly the same yield of lettuce. Here you've got the result with the complemented aquaponics, and you can see that we have an increase of yield of nearly 40%, which is really promising. Concerning the root growth, we observe a higher volume and a higher weight of dry weight and fresh weight of roots for lettuce grown in aquaponic system and in complemented aquaponics. If you remember, how to explain that? If you remember, the concentration in aquaponic system is very low. So how can we have at least the same yield of lettuce? So we suspect that organic acid or microbiota, microorganisms, are involved in such phenomenon. Let's move now to the second part of other research, plant disease control. in aquaponics, it is very difficult to use pesticides because in Europe, when you rear fish, you're not allowed to use pesticides. And at the same time, in opposite, if you use plants, you're not allowed to use antibiotics. So if we have some pathogens for plants or for fish, how can we control them? And for plant pathogen, until now, there is only preventive cultural practices or physical water treatments. But of course, there is no possibility to use pesticides, as I've already said. So we decide to work and to see if we can develop some alternative methods. In the literature, it is said that fish effluents are able in vitro to protect, to have some effect against plant pathogens, kind of suppressive effect. And the question, is it an antagonistic effect or plant elicitation? So the aim of our experiments are to evaluate the aquaponic water suppressiveness towards plant pathogens. And in our place, we did it first in vitro, with in vitro studies, and it was done with Pythium. Pythium, this is a pathogen. It's able to really create big damage on small plants, on small lettuce. And we control also the effect of aquaponic water on lettuce and on the symptoms of the lettuce. Let's see, and let's move directly to the results. You can see with our trials in vivo that hydroponic water is, the roots are really less, and you can see that they are already start to turn brown. So it means that it reveals the presence of the pathogens of Pythium. In opposite, on aquaponic water, we didn't observe such a problem. And you can see that there was a statistical difference between symptoms in aquaponic water versus hydroponic water. So again, how to explain that? How to explain these results? When we filter the aquaponic water to get rid of the microbial, the microorganisms, we are losing the suppressive effect. So it means that microbiota, microorganisms might be involved. So let's move very quickly to the last part I want to show you. It's the microbiota characterization. Here, I want to present two approaches. The first one is on our puff box. Again, the marine container with on the roof, the greenhouse. When we start, we don't have a lot of idea in the scientific community about the composition of the microbiota, about the structure of the communities. Does it evolve or is it static? So you see here a photo inside the puff box. We decide to sample once a week here in the sump and also in the biofilter, the water, and we analyze the water with high-throughput sequencing. I don't know if you're familiar with it, but it's able to prospect and to highlight the diversity of the different microorganisms thanks to sequencing, Illumina mini sequencing, and also thanks to computer bioinformatic analysis on time. So the results. This is the biofilter, this is the sump, and you can see week by week the evolution of the microorganism. Again, it's here, you can find the publication. You can see that there is a diversity in terms of taxa. So each color represents a taxa, and there is a big difference between biofilter and sump. In opposite, if you see one compartment, for example, the sump, you don't see week by week a big evolution. So we can conclude that there is different communities in one system. So the biofilter community was most diverse in our case, and the community looks stable over time. But of course, we did only 3 weeks, and we are working now to enlarge the time and to have a larger period to see the dynamic of the communities. The second approach was to sampling some and biofilter in different other systems and compare it with our PAVBox. So system in Germany, system in the Netherlands, and several systems in Belgium. I won't show you the graph, but just some conclusions, important one. Here, several taxa are predominant in the different systems, and we could find some taxa which are able to degrade organic molecules. Be careful, because I'm speaking about potential functions. We didn't demonstrate that. We only highlight the different taxa, and searching in the literature, we know that they are associated with some functions. We also discover some taxa which are associated with plant, and in particular root association. And among other, you can see that we discover this genus. And we also observe some microorganisms that are implicated in the nitrogen cycle. Okay, we were also able to highlight a core taxa. A core taxa means that you can find the same taxa whatever the system. So in our 7 different systems in the 3 countries. And this core taxa, we can find inside this core taxa an important proportion that are usually found in soil and rhizosphere. And moreover, some taxa are known to protect plants against fungal disease. And maybe that could explain why we observe suppressiveness of aquaponic water against Pythium. Of course, we are still working to characterize aquaponic rhizosphere and to understand the function of the microorganisms. But anyway, you can find also some data of this presentation on this article. So I would like to thank all my teams first, which were very, very active on our projects. So I was speaking about Smart Aquaponics, and Pierre Rollier is very active, is the operational coordinator, and Benoit, yes, Benoit here, Benoit Stalport is a PhD student who is modeling Smart Aquaponics. Gilles Stubenker is working on suppressiveness of water, of aquaponic water, and Mathilde here, she's working on microbiota. And of course, the microbiota is very, very, it's not an easy discipline, and she's framed by Sébastien Masser. And Jimmy Bean, it's also important, it's a technician. He's taking care about the PAVBox, about the sapristi, all the aquaponic system. And to finish, I want to thank all of you to listen to me, and I hope the quality of the song was good. Thank you.
Thank you very much, Haissam. Fascinating presentation. I have prepared some questions for you, but actually there are so many questions from the audience that I would like to move straight on to those questions.
Okay.
You can see them in the Ask a Question room, and I will try to invite some of the speakers to the floor to ask the questions themselves. And actually, Danny have posed his question already before we started the webinar. So Danny, I will invite you to the screen to ask the question. If it doesn't work, I will just read the question. Let's see if it works. And his question is about energy and aquaponics. I think you can also see this question.
Yes. So the question is, running smart aquaponics with sensor requires a lot of power. So I would say that even without sensors, it's required power. Smart aquaponics system, as I told you in the beginning of my talk, is able to preserve water and is also able to save fertilizers. But to run the system, you need pump for the water to circulate. And this requires energy, of course. And if you want to grow plants inside the greenhouse, you need also to eat the greenhouse. If you want to rear your fish on aquaculture system, again, sometimes you need some energy. So I think it is very, it's a very smart idea to use alternative method to produce energy like solar system. Yes.
Okay, great, thanks. Danny, I hope it answers your question. I see that you cannot join because you're not dressed properly yet, so let's do it here. I see also a question from Jan Jacob. I will try to invite Jan Jacob to the screen. Are you there? Can you join us? Let me see.
But I can read the question and answer.
Yes, we can do that as well. I thought it would be nice to see some of the people who are joining the meeting.
Yes, he said he's saying that he's not plugged into video, so.
Okay, no worries. Then let's go without inviting people to the screen. So
Okay.
the question from Jan Jacob is, where would aquaponics grow? Growers acquire the necessary microbes to filter the water? And are those filters available from commercial providers?
Yes. First of all, you're not obliged to put inoculant in your system. In our case, for example, for the PAF box, we first run the system just with the fish. And there is a natural microbiota coming from the fish that are able to transform ammonium in nitrate and then nitrate. So if you are patient enough, you don't need to have extra microorganisms. In some case, in industrial case, in the industry, you can add some inoculants. That's possible.
Okay, great. I see there is a question voted 4 times, so I see that there are more people who would like to know the answer. It's questioned by Siddharth. Is it possible to combine the techniques of aquaponics in combination with vertical farming?
Okay, that's a big question because, first of all, what is the definition of vertical farming? The vertical farming can have several phase, I would say. First one is indoor farming without any light. But what is important is to have different layer of culture. This is what it makes vertical. You can have greenhouse on a rooftop. It's also vertical farming. There is no difficulty to have vertical farming with aquaponics. If we see our PAF box, it's like a vertical farming. And there are some in the world, like in US, for example, there are some aquaponic system in total indoor system. So without any light, without any natural light. So I would say that yes, aquaponics is compatible with vertical farming. But we have to be very, very careful concerning economics. Because when you use vertical farming, you use high level technique. And it means sometimes also that you increase the cost. So when you do that, you have to be very, very careful about economics, and is it economically feasible to build a big system which costs a lot, and at the end you just produce lettuce and fish and not big precious things. So it's compatible, but we have to be very careful concerning economics.
So there's no simple answer. Yes or no?
No.
Great, thank you. Another question from Emil. If additional nutrients are needed, can we speak about circular system? Could the addition of nutrients be provided via other animals or plants?
Okay, it's also it's a good question. First of all, as I presented at the end of my talk, for some varieties of plants, aquaponic system gives the same level as hydroponic system, even if you have less nutrients. So that's great, but it doesn't work with every variety or every species. And in many cases, to have the same yield as in hydroponic, you need to complement with additional nutrients. I would say that it's then partially circular economy, because if you add 50%, but it means that at least you are autonomous for the other 50%. So it's already a step. Then we are working also in our laboratory to what we call bioponics. It means that we try to find the fertilizer from other organic material. It can come from plants, it can come from other animals, and then our target is to really get rid about chemical fertilizers. And if we succeed, we would be able to say we are 100% in a circular economy.
Okay. See that there is also in the chat, there's interesting conversation going on between Josop and André. But I would like to move to another question. I see that there are quite some questions about pathogens. One by Anne and another one about E. coli by Jan. So you mentioned Pythium in the pathogen section. Do you already have more experience with plant pathogens in aquaponic system? And then how would you get rid of unwanted microorganisms when they are detected in the system?
Okay. So management of aquaponic systems concerning pathogens plant pathogen is difficult, because as I said, we are really poor in authorized tools to protect against these pathogens. If we start with Pythium, it is because we had the feeling that in our systems, we didn't observe a lot of pathogens in aquaponic system. It was not with scientific data, just with observation. So it means that aquaponic system seems to protect by itself against pathogens. And this is why, in some cases, we don't have any pathogens. No, if I speak about the PAVBox example, we run the PAVBox for 8 years now. If we stop in end of September, beginning of October, we start to see some disease, but associated with cooler temperature, higher relative humidity. And we observed some pathogens when we were in the system all year round. This is why now we decide only to go with cold system. So we believe that we need really to still work on developing tools which are not chemical pesticides, but like we show now some microorganisms, and then we will be able to protect plants against pathogens. Another point is concerning microorganisms. I'm not specialist about insects, so I won't speak about insects, but concerning plant pathogen like fungi or bacteria, you can use also physical treatment like UV treatment. We do that in the Suppressive to control and to keep the level of microorganisms very low, and we hope that we get rid about pathogens.
Okay, thank you. Another question of a very different type. So one is about whether the system, how autonomous the system is, how much labor it requires, and also can it be operated by elderly people?
Huh. I don't know if you're familiar. It's really depending again on the expectation. If we go to an industrial production, it's like industrial aquaculture or industrial hydroponic system in greenhouse. And then, of course, a lot of part of the system is automated. So it means that you don't need a lot of people per hectare, for example, or per system. Of course, you still need people to pluck, to harvest tomatoes, for example, or lettuce and so on. So it's still labor consuming in that part. Now, if we go to lower techniques, lower level of techniques, it can consume more labor, and it's really depending on the level of how your system is automated or not. And concerning elderly people, it can be managed, it can be also handled by elderly people, yes. You need, of course, to frame them, but it's possible. And again, it's really depending about your goals, and if you need really big production, optimized production, and you count every cent or not.
Okay, thank you for this answer. I see that in the Ask a Question room, there is still need for some more information about actually circularity and combination of aquaponics with plant production. So one question is, would you see, that's a question from Chris, would you see insect rearing as a positive contribution to aquaponics system? And an idea is insect feces could be used in anaerobic digestion for electrical power, and the insect can be fed from the vegetable waste and other organic waste.
Okay, I didn't think about insect feces to produce energy, but we think about insect rearing to feed the fish, indeed. And we tried for the first time, I didn't show, because we don't have a lot of time, but I didn't present it. We just finished a first experiments with our colleagues from entomology laboratory, and they are able to rear some insects that produce a lot of proteins. And we give them to our trouts. We are rearing trouts sometimes in our system, and we compare the growth of the trouts with conventional feeds and feed including insects, and we had good results. So that's a possible things to do, is to include in the circular economy insect as part of the system to feed the fish. And of course, with that, thanks to that, you don't need to find proteins from other fish, for example. And an important point is the diet of the fish. You have omnivorous fish and carnivorous fish. Omnivorous fish, you need only 30% of proteins in the diet, daily diet, and it's 40% for carnivorous. So then, of course, if you work with carnivorous, you need to increase the protein ratio, and then, of course, insects can be part of the solution.
Okay, great. I had to unmute myself. And then another question in this series is about, well, the question is, I want to know about extensive production of fish, the quality of nutrients in water. Is it enough to supply vegetables and herbs demand? And then there is another question about the ultraviolet treatment, if it could kill the good microorganisms and reduce the good points of aquaponics. So 2 questions in one from Gabrielle.
So concerning extensive aquaculture, of course, if you have less fish per cubic meter, then you will have less concentrated sludge and then less concentrated nutrients available for the plants. A possibility is to concentrate this water, but again, it costs energy. Then another possibility is to complement this water with extra fertilizer. You add other fertilizer coming from chemical part, or even as we start to try from organic sources. Concerning UV, it's a good question because the water is circulating all around the system. And it's really depending where you put your UV light. As I presented at the end of my PowerPoint, you can see that depending on the compartment of your system, you find other microorganisms. So it means that some microorganisms are able to fix on some material support, on some material. So it means that they don't move all around the system. So it means that you can still preserve your good bacteria, your good microorganisms in such compartments.
Okay, great. I think we have time for 2 or 3 more questions. So I would ask everybody to vote the questions you would like to be answered. And I see one sweet question from Siddharth. What could be the smallest scale for successful aquaponics?
What would be the smallest
scale for successful aquaponics?
I don't understand really the question. The smallest size of aquaponic system?
I think so, yes. That's how I would understand it.
Okay. There is no simple answer. It's really depending on your goal. If you just want to have a small system for in your garden, in your backyard, why not? Then you don't mind about the size. It can even be a little pot with the water and there is some system like that which is working well. Of course, if you are an enterprise and you want to earn money, you need a bigger systems, and of course it's really, but then again, it's really depending on your goal. If I go back to the example of the chef, I present a small enterprise, which is a restaurant, which is able now to produce fresh fish and plants. On itself, he doesn't earn money with this. It's just nearly at a break even. But for him, there is no, it's not really important, because what is important is the added value when he cook. And of course, if you go at an industrial scale, then you need bigger systems. But there is no simple answer to say, okay, from that size to that size, it's for education. From that size to that size, it's for a small company or for industry. It's really depending on also on how the system is developed, or how the system is managed, and what are your crops. Is it really high value crops? Or, lettuce, it's 30 cents, but the basilic is 2-3 euros. And it occupies the same space. So it's really depending on the value of your crop and your fish also.
Okay, great. There was a question I saw that many people wanted to know answer. It's from Terlach. You mentioned bioponics. Is it possible to use nutrient supplement from recirculated and filtered black water, gray water, sewage water?
I don't know. We didn't yet experience all this water, but I think we could try. We have to be, of course, we really have to take care about potential sanitary problems. If you go with dark water, as we call it here. But I think we have to try that. It's a good idea.
Okay. I don't know the abbreviation, but it's a question from Cole. How much did the PAFF cost to create?
We speak about just the material is more than several thousands euros. So the idea to have it as a system for the urban community is maybe a little bit too optimistic. And now we are using it as a demonstrative tool and also to make research. But of course, we had in mind so no more simple way to build a system and maybe less expensive.
Okay, great. I would like to finish maybe with two last questions. Somebody of actually Siddharth is asking, can human urine be used as organic matter on large scale in a city or in town?
I didn't understand the question. Can you repeat?
The question is if you can use urine as an organic matter in aquaponics.
Yes, we could. In principle, we didn't test it, but urine is based on nitrogen, and you know that urine is one of the fertilizer used in standard or conventional agriculture. My only concern is about fish, so see what is the level of concentration of urine which is not toxic for the fish and so on. But there are some fertilizers for conventional agriculture based on urine. Yeah.
Okay. And then the final question, when the smart aquaponics system will be ready?
So the application will be ready at the end of 2021.
Okay.
So 18 months, I would say. if there is no problem. Yeah.
Okay. And then it's on commercial scale. Can we buy it, or how it will work?
We are thinking about that. There will be a free version
Okay.
with several functions, but not all the functions. But we are thinking about how to sustain the system, because of course the application, we have to maintain the clouds, the computers, and so on, and it costs. So we need to see how we can maintain all these things, and maybe we will go for commercialization of part of the application.
Okay. So this version ready in 2021. It will be the final version, or it's going to be a beta version?
The beta version will start end of 2020 and will run 1 year.
Okay.
And normally we're supposed to have the final version at the end of 21.
Okay, so JC, that's the answer to your question. Wow, I am really surprised. Possible and final question, yeah. Well, thanks a lot for all your questions. Amazing participation. I have posted a poll also to ask how useful the presentation was, and I got a positive feedback from almost everybody who joined the webinar. So thank you very much, Haissam. Sorry everybody for the technical issues at the beginning. I hope it didn't affect too much your experience. And we'll have another webinar halfway May. So check our website, Urban Greenhouse Challenge events. We'll post soon the information about what webinar it will be and at the exact time. And I would like to finish now and thank everybody for joining, and thank you very much, Haissam, for the presentation and all the effort you have put in it. See you next time, and have a good day, everybody.
Bye-bye.